Hello and warm welcome to our presentation. Today we are excited to introduce our project TumorLytix. Let's begin by diving into what TumorLytix is all about. What is TumorLytix? TumorLytix is our answer to a pressing challenge in medical imaging. It's an advanced framework that detects and segments brain tumors without the need for large annotated data sets. So the motivation behind the TumorLytix is like why TumorLytix is needed. Here's the challenge. Over the 90% of the current brain tumor segmentation models require large manually annotated datasets. This process is not only expensive but also highly impractical on a large scale. Radiologists spend hours annotating each scan, and scaling this effort to thousands of patients is unrealistic. And also, there was a recent survey on deep learning for brain tumor segmentation topic, which highlights the unsupervised and semi-supervised methods as promising alternatives. By using the smaller labeled datasets and synthetic augmentation, these approaches can significantly reduce the reliance on manual annotation. So now let's dive deeper into the problem statement behind the TumorLytix. The current challenge, what we are trying to solve, is pretty clear. We need a tool that can detect and segment brain tumors accurately without relying on the labeled data. So to do this, TumorLytix combines the power of advanced models, that is CycleGAN and the diffusion model. And the goal is pretty simple: to create a scalable, efficient and accurate tool that works in real-world clinical environments even when the label data is scarce.
Tackle this problem in three stages: paired generation, conditional diffusion, and segmentation. We will go through each of the stages in detail in the upcoming slides. First, we perform paired generation, meaning we generate paired healthy tumor brain MRI scans. We achieve this using state-of-the-art CycleGAN model. Now, how do we do this? In CycleGAN, we have two domains. As you can see in the diagram, healthy and tumor. We aim to learn the features of one domain and transfer it to the other. For example, we learn features of tumor regions from tumor scans and generate tumor textures on the healthy scans, thereby generating paired data. It works on a simple architecture: generator and discriminator. For each domain, we have the generator that generates corresponding domain paired images, while the discriminator detects whether it's fake generated or a true image. The generator gets better by fooling the discriminator, and the discriminator gets better by identifying fake generated images. This process continues both ways, and we generate healthy to tumor and tumor to healthy images, completing the cycle as mentioned in the name. To achieve this task, we collected over 1500 healthy brain MRI scans and about 3000 tumor affected scans. On training our model, we successfully generated the required paired data, as seen in the diagram. We trained our model for over 75 epochs and achieved a high accuracy of 88.2% in generating tumor images. However, CycleGAN was poor in reconstructing healthy images from tumor. We deciphered the following possible reasons: mode collapse, where CycleGAN is unable to represent abnormal features like tumors, leading to reconstruction errors. Most of the time, CycleGAN generates implausible features, which are unreliable in critical applications like medical imaging. Last but not the least, CycleGAN lacks the fine detail required to achieve accurate segmentation. Our literature survey helped us identify diffusion models as a promising alternative for the same.
Moving on to the next phase of our approach is the diffusion model. The diffusion model is designed to reconstruct healthy versions of tumor-infected brain images for anomaly detection and segmentation. The backbone of a model is improved UNet architecture. Our model uses a time-dependent noise schedule to add and remove noise during the forward and reverse diffusion process. As seen here, during the forward process, noisy versions of tumor images are generated by combining Gaussian noise with the original image. The Gaussian noise is introduced to the input tumor-infected images step by step. This generates noisy version of image, stimulating real-world noise. The noisy image along with healthy reference image is used to input for reverse process. The reverse process then learns to denoise these images, reconstructing the original tumor infected image from noisy version. This reverse mechanism models the joint probability distribution of noisy and clean images, enabling effective denoising and reconstruction. Our dataset includes paired MRI scans, one set of normal brain scans, and another of tumor injected images. These pairs are generated using CycleGANs, stimulating realistic tumor textures to augment training and improve the model's robustness. After training, here's what we have achieved. The results showed an impressive accuracy of 92.17%, demonstrating the model's capability to generate reconstructed images from noisy inputs. The loss curve shown here highlights consistent improvement over training, with the loss steadily decreasing across epochs.
Now moving on to the third phase, which is the segmentation. The segmentation process is designed to pinpoint and highlight tumor areas in medical images. It works by comparing the original tumor image with a healthy version of the image created by the diffusion model. By calculating differences between the two, the method identifies abnormal regions, that is the tumors, and creates a refined mask to clearly show where the tumor is located. So in the given images, the first is the original tumor image, which we are referring from the CycleGAN. Second is the reconstructed healthy images, which is generated by the diffusion model itself. And the third image shows us about the anomaly map, which is pixel-wise difference between original tumor and reconstructed healthy image. The fourth and the most important part is the segmentation mask. This is a binary mask created by applying a threshold to the anomaly map. Pixels above the threshold value are marked as the main area of the tumor region, while others are being excluded. This mask is further refined using various operations to remove noise and improve accuracy.
To compare our results and evaluate on metrics, we generated ground truths for a sample of 5 images by manually labeling the tumor regions, as shown in the diagram.
After creating the segmentation mask, we apply it to both the CycleGAN and our combined approach. The results show that the combined approach, which uses a diffusion model, performs better. This is because the diffusion model provides more accurate reconstructions of healthy images, leading to a more refined and effective segmentation mask.
Now to evaluate the output of the two models, we have used 3 evaluation metrics. First is the dice coefficient, second is precision, and third is recall. Now as we can see in the bar graph, our combined model has outperformed CycleGANs in the majority of the cases, hence showcasing the greater accuracy and completeness in predictions. After successfully implementing 2 models, we have observed that the combined approach using diffusion is better than CycleGANs in the following areas. The first is the performance evaluation. We can see the diffusion has performed better than the CycleGANs. In terms of enhanced segmentation, diffusion model excel in refining segmentation mask and detecting subtle anomalies, addressing the limitation of CycleGANs in specific areas. For the combined approach, integrating CycleGANs and diffusion model, we have improved the accuracy of detecting tumor boundaries and regions. Now these models use supervised learning, which means they don't need label data, making it possible to accurately locate tumors with only partial data or simulated data, that is pseudo-paired data. For future work, we can extend the work in classification of the tumor. We can also use this for multimodal MRI scans, and for clinical context, we can also integrate more data specific for the patient, such as age, genetics, or tumor grade, which can help to improve the contextual relevance for segmentation results. Thank you and hope you liked it.